July 12, 1942. The floor of Factory No. 183 in Nizhny Tagil trembled with the rhythm of industrial war. 19 automatic welding machines screamed in synchronized chaos, their arcs blazing beneath mounds of granular flux. Each machine moved along the seam of a T-34 tank hull, depositing metal at speeds that seemed impossible. The air hung thick with ozone and the bitter smell of molten steel. Then, without warning, one of the hulls split. The crack started at the forward glacis plate, where armor met armor. It propagated diagonally across the weld seam, racing through hardened steel like lightning through summer sky. Within seconds, a 1,500mm fracture had consumed what should have been the strongest section of the tank. The hull was ruined. 3 days of work, several tons of precious armor plate, and one desperately needed tank, all rendered useless. Workers stood frozen, watching their efforts disintegrate before the metal had even cooled. This was not an isolated incident. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Throughout the summer of 1942, crack formation plagued Soviet tank production with epidemic ferocity. At Factory 183 alone, between 20 and 30% of hulls developed structural failures during or immediately after welding. Some cracks appeared while the metal still glowed orange. Others materialized hours later, snaking through armor that appeared perfect moments before. The hardened steel, designated as 8S armor, chosen specifically for its resistance to German anti-tank rounds, was tearing itself apart under its own internal stresses. The timing could not have been worse. The German 6th Army was pushing toward Stalingrad. Panzer divisions were cutting deep into Soviet territory, destroying tanks faster than factories could replace them. The Red Army needed 2,000 T-34 seconds per month to maintain numerical superiority on the Eastern Front. In July 1942, they were barely producing 900. And of those 900, nearly 300 were being rejected or failing in the field due to welding defects. Traditional hand welding could not meet the demand. A skilled welder, working methodically with stick electrodes, required 12 hours to complete the hull seams on a single T-34. Factory 183 employed over 300 welders working in rotating shifts, and still production crawled. The mathematics were brutal and unforgiving. At current rates, Soviet factories would need 18 months to produce enough tanks for a single major offensive. The war would not wait 18 months. In Kiev, before the German invasion, Professor Evgeny Oskarovich Paton had been perfecting a technology that military engineers considered experimental at best, reckless at worst. Automatic submerged arc welding, developed at his Institute of Electric Welding in 1939, used a continuously fed electrode buried beneath a blanket of granular flux. The flux melted, protected the weld pool from oxidation, and then solidified into a slag cap that could be chipped away. The process was fast, consistent, and required minimal operator skill. A single machine could deposit weld metal at 5 times the rate of the most experienced hand welder. But there was a fundamental problem that had prevented military adoption. Automatic welding was designed for mild steel, the soft, ductile material used in bridges and pipelines and civilian construction. Tank armor was the opposite of mild steel in every way that mattered. 8S armor was heat-treated to surface hardness approaching 60 Brinell, making it resistant to penetration, but also brittle and prone to cracking under thermal stress. The rapid heat cycling of automatic welding, with its sustained high amperage and continuous feed, created precisely the conditions that made hard armor fail. Every attempt to adapt automatic welding to armor plate had ended the same way. Test welds looked acceptable when hot. They passed visual inspection. Then, as the metal cooled and internal stresses locked into the crystalline structure, cracks appeared, sometimes small, sometimes catastrophic, but always present. The Central Scientific Research Institute, known as TSNII 48, had spent 2 years trying to solve the cracking problem before the war began. They had failed. Military procurement officers had written off automatic welding as unsuitable for combat vehicles. Hand welding, slow and labor-intensive but proven, remained the standard. Then, on June 22, 1941, Germany launched Operation Barbarossa. The German advance was so swift and devastating that Soviet tank arsenals found themselves directly in the path of panzer divisions. In an operation that would define Soviet industrial resilience, entire factories were evacuated. Machine tools were dismantled, loaded onto rail cars, and shipped east to the Ural Mountains. Workers and their families followed. At the Comintern locomotive plant in Kharkov, engineers had 72 hours to evacuate tank production. They succeeded, barely, moving everything portable 1,500 kilometers to Nizhny Tagil. There, in makeshift facilities with dirt floors and partial roofs, they restarted T-34 production in December 1941. The conditions were medieval. Winter temperatures dropped to 30 below zero. The factory building had walls but no windows, no heat, no proper lighting. Workers assembled tanks wearing every piece of clothing they owned, their breath visible in clouds of frozen vapor. Production rates were dismal. In December, the Nizhny Tagil factory completed 37 tanks. In January, 64. In February, 102. But the Red Army needed thousands. Professor Peyton arrived in Nizhny Tagil in July 1941 as part of the Institute of Electric Welding's evacuation. He was 51 years old, a distinguished academician who had spent his career studying the fundamental physics of welding processes. His automatic submerged arc welding system represented 15 years of research into arc behavior, electrode composition, and flux chemistry. He knew the technology worked for mild steel. He believed, with the fervor of a scientist who has glimpsed an elegant solution, that it could work for armor plate if the underlying metallurgy could be understood and controlled. The problem, as Peyton explained to increasingly desperate factory managers, was hydrogen. When electric arc welding melts steel, it also dissociates moisture in the air and in electrode coatings. Free hydrogen atoms, tiny and mobile, diffuse into the hot metal. In mild steel, this causes porosity, small voids that weaken the weld but rarely cause structural failure. In hardened armor plate, hydrogen creates something far more insidious. The atoms lodge in the crystal lattice of the steel, creating intense localized stresses. As the metal cools and contracts, these stresses concentrate. The hardened microstructure, unable to deform plastically to relieve the stress, fractures instead. This phenomenon, called hydrogen-induced cracking or cold cracking, manifested hours or even days after welding. A hull could pass inspection, be moved to the assembly line, and then split without warning as residual stresses found weak points. The cracks typically originated at the heat-affected zone adjacent to the weld, where the armor's heat treatment had been partially undone by welding temperatures. This region, softer than the base armor but harder than the weld metal itself, became a stress concentrator. Once a crack initiated, it propagated through the brittle structure at frightening speed. Previous attempts to solve hydrogen cracking had focused on preheating and post-heating the armor. If the steel was heated before welding and kept warm afterward, hydrogen could diffuse out before internal stresses reached critical levels. This worked, technically, but required enormous infrastructure. Each hull would need to spend hours in heating ovens before welding, and more hours afterward. The time and energy requirements made mass production impossible. Factory managers rejected the approach immediately. They needed tanks now, not carefully baked experimental prototypes. Peyton took a different path. Instead of trying to prevent hydrogen from entering the steel, he worked to minimize how much hydrogen was available to enter in the first place. The key was the flux. Standard flux formulations used for mild steel welding contained compounds that released moisture when heated. This moisture dissociated in the arc, producing the hydrogen that caused cracking. If the flux could be redesigned to eliminate moisture-bearing compounds and create a protective atmosphere that excluded air, hydrogen pickup could be reduced to levels that even hardened armor could tolerate. Working with Vladimir Ivanovich Dyatlov, a metallurgist who had been evacuated with Ts NII-48, Peyton reformulated the flux composition. They eliminated calcium carbonate, which released carbon dioxide and water vapor. They increased the proportion of calcium fluoride and manganese oxide, which melted to form a dense, impermeable slag that sealed the weld pool from atmospheric contamination. They added metallic deoxidizers, primarily ferromanganese, to scavenge any oxygen that might reach the weld. The electrode wire presented another challenge. Standard welding wire was mild steel with carbon content around 0.1%. When this wire deposited into a weld pool surrounded by hardened armor containing 0.4% carbon, the resulting weld had an intermediate composition that remained too hard and crack-prone. Dyatlov proposed using low-carbon electrode wire, essentially pure iron with carbon below 0.05%. The low-carbon filler metal would dilute the high-carbon base metal, creating a weld deposit, all softer and more ductile than the surrounding armor. The combination, low-carbon wire and redesigned flux, was tested in February 1942 on small test plates. The results were encouraging but not definitive. Welds showed reduced cracking compared to previous attempts, but cracks still appeared in approximately 15% of samples. Peyton suspected the problem was not the welding process itself, but the residual stresses built into the hull structure during assembly. Tank hulls were complex, three-dimensional structures with multiple intersecting plates welded at various angles. Each weld contracted as it cooled, pulling and distorting the surrounding structure. By the time a hull was complete, it carried millions of pounds of locked-in stress. He proposed a radical revision to the entire assembly sequence. Instead of welding hulls in their final three-dimensional configuration, prefabricate major sections, flat or in simple geometric forms that allowed stress to dissipate naturally. These sections would then be stress-relieved through controlled heating before final assembly. The final joining welds would lock in much less residual stress, making hydrogen cracking less likely. Factory managers were skeptical. Prefabrication meant reorganizing the entire production floor, retraining workers, and implementing quality control at multiple stages. But with crack rates approaching 30% and production falling further behind demand, they had no better alternative. In April 1942, Factory 183 allocated a section of the production floor for experimental assembly using Peyton's methods. The first test hull was fabricated from 6 major pre-welded sections, each stress-relieved in improvised heating ovens before final assembly. Peyton's team used their modified flux and low-carbon electrode wire. The automatic welding machines, repositioned to accommodate the new assembly sequence, completed the major seams in 4 hours, rather than 12. The hull was then allowed to cool slowly, monitored constantly for crack formation. 36 hours passed. No cracks appeared. Inspectors used magnetic particle testing, a technique where iron powder and magnetic fields revealed microscopic surface defects. The welds were clean. Ultrasonic testing, bouncing sound waves through the metal to detect internal voids, showed full penetration with minimal porosity. The hull was loaded onto a test rig and subjected to flexural stress exceeding normal combat loads. It held. The breakthrough, tentative and fragile, had arrived. By July 1942, 3 automatic welding machines were operating at Factory 183 using Peyton's system. Each machine was tended by a single operator, whose primary job was to monitor feed rate and move the machine to the next seam. No special welding skill was required. Women and teenagers, pulled from collective farms and given 1 week of training, could operate the machines as effectively as experienced welders. This single innovation solved 2 problems simultaneously. It accelerated production and freed skilled welders for tasks that could not be automated. The production numbers began to shift. In June, Factory 183 produced 312 tanks, with a rejection rate of 28% due to welding defects. In July, with automatic welding on 3 machines, production increased to 394 tanks, with rejections dropping to 18%. In August, 6 machines were operational. 571 tanks rolled off the line, rejection rate 11%. The trend was undeniable and accelerating, but the transformation revealed a new problem that nobody had anticipated. The automatic welding process worked flawlessly, but the armor plate itself was failing in unexpected ways. The 8S armor specification called for surface hardening through a process called face hardening, where one side of the plate was rapidly heated and quenched while the back remained softer. This created a hard outer shell resistant to penetration, backed by tougher material that prevented brittle fracture. But the quality of armor plate arriving at Nizhny Tagil varied wildly. Some plates had insufficient hardness, others were too hard. Some were incompletely hardened, with soft spots that compromised ballistic protection. The problem traced to the steel mills in Magnitogorsk and Chelyabinsk. These massive facilities had been running continuously since 1941, producing armor plate as fast as furnaces could heat and rolling mills could shape. Quality control had collapsed under the pressure of wartime demand. Chemical composition varied from heat to heat. Thickness tolerance was measured in centimeters rather than millimeters. The hardening process, which required precise temperature control and timing, was being done by eye and experience rather than instrumentation. Plates that should have been rejected as substandard were being shipped to tank factories because rejecting them would mean missing production quotas. Dyatlov and his team at TSNII 48 spent the late summer of 1942 developing inspection protocols that could catch defective armor before it reached the welding line. They used Brinell hardness testing, pressing a hardened steel ball into the armor surface and measuring the indentation diameter. Plates that fell outside the specification range of 55 to 65 Brinell were rejected and returned to the mill for retreatment. They used magnetic analysis to detect incomplete hardening, which left characteristic patterns in the steel's magnetic response. These inspections added time to the production process, but eliminated the catastrophic failures that occurred when defective armor was welded into hulls. By September 1942, the automatic welding system was producing results that seemed impossible months earlier. 10. Welding machines operated at Factory 183. 736 T. 34 tanks were completed. The rejection rate had dropped to 4%. Each machine could complete a full hull in roughly 4 hours, including setup time. The productivity increase compared to hand welding was not merely incremental but exponential. A single automatic machine replaced 5 skilled welders, and it could run continuously with operator changes rather than stopping for breaks and shift changes. The human logistics were equally revolutionary. In July 1942, Factory 183 employed 280 skilled welders. These workers, predominantly male and trained before the war, were a finite and depleting resource. Combat losses, disease, and exhaustion were eroding the skilled labor pool faster than training programs could replace it. By October, with automatic welding handling the majority of hull fabrication, the factory employed only 85 skilled welders for specialized work that still required hand welding. The 200 workers freed from welding were redeployed to assembly, painting, and engine installation, accelerating the entire production line. The operators of automatic welding machines required minimal training and no special physical strength. Women comprised 70% of the automatic welding workforce by November 1942. Teenagers as young as 16 operated machines after 1 week of instruction. The work was still dangerous. The arc's ultraviolet radiation could cause painful burns, and the fumes were toxic, but it was less physically demanding than hand welding and more forgiving of inexperience. This democratization of skilled labor was as important to Soviet tank production as the speed improvement. The cost reduction was equally dramatic. In 1941, a T-34 tank cost the Soviet state approximately 270,000 rubles to produce. By the end of 1942, with automatic welding reducing labor hours and improving yield, the cost had dropped to 193,000 rubles. This 28% cost reduction meant the same resources could produce more tanks. Over the course of 1943, costs would fall further to 135,000 rubles per tank, a 50% reduction from early war production. The German intelligence services, monitoring Soviet tank production through aerial reconnaissance and captured documents, noticed the production surge but misinterpreted its cause. German analysts assumed the Soviets had simply thrown more workers and more factories at the problem, brute force industrial expansion characteristic of Soviet central planning. They failed to identify the technological transformation underlying the production increase. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German tank manufacturers continued using hand welding exclusively, considering it the only method suitable for armor plate. This technological conservatism would prove costly. The scale of the transformation became visible in the production statistics that Soviet planners tracked with obsessive precision. In 1941, before automatic welding was implemented, Soviet factories produced approximately 2,800 T-34 tanks. This was considered an achievement given the chaos of factory evacuations and the loss of Western industrial centers. In 1942, with automatic welding gradually spreading across multiple factories, production reached 12,553 tanks. In 1943, the year automatic welding reached full implementation across the Soviet tank industry, production exploded to 15,700 units. The monthly average in 1943 was 1,300 tanks, or approximately 43 T-34 seconds completed every single day. This meant Soviet factories were producing a new tank every 33 minutes, around the clock, for an entire year. The Germans, using traditional hand welding and craft production methods, were producing approximately 2,400 tanks and assault guns combined across all models in 1943. Soviet T-34 production alone exceeded total German armored vehicle production by a ratio of 6-1. But the numbers alone do not capture what made automatic welding genuinely revolutionary. The transformation was not merely quantitative but qualitative, reshaping how the Soviet Union thought about industrial warfare. Traditional tank production required craftsmen whose skills took years to develop. These workers were irreplaceable assets, whose loss directly impacted production capacity. Automatic welding decoupled production capacity from skilled labor availability. A factory could lose experienced workers to conscription, disease, or combat casualties, and maintain production by training replacements in days rather than years. Factory number 183 in Nizhny Tagil exemplified this transformation. In July 1942, when automatic welding was first implemented, the facility employed 280 skilled welders, producing approximately 400 tanks monthly. By January 1943, the facility employed 57 workers operating 19 automatic welding machines and produced over 900 tanks monthly. The productivity per worker had increased by a factor of 11. This was not incremental improvement through practice and optimization. This was a fundamental restructuring of industrial capability. The automatic welding machines themselves were remarkably simple devices, a testament to Patton's engineering philosophy that reliability mattered more than sophistication. Each machine consisted of a motor-driven spool that fed electrode wire at a controlled rate, a contact tip that conducted welding current to the wire, and a hopper that dispensed flux ahead of and around the arc. The entire apparatus, mounted on a wheeled carriage that rode on rails, welded temporarily to the workpiece. An operator set the feed rate and amperage, started the machine, and walked alongside as it progressed down the seam. When the seam was complete, the operator stopped the machine, chipped away the slag, inspected the weld, and repositioned the machine for the next seam. The simplicity was deliberate. These machines had to function in factories that were barely more than covered spaces with electrical power. Maintenance had to be minimal because spare parts were scarce. Operators had to be able to diagnose and repair common problems without specialized training. Patton designed the system around the assumption that everything would break and everything would be misused, so robustness trumped elegance. The feed mechanism used gravity and friction rather than complex gearing. The contact tip was a consumable item that could be replaced in minutes. The flux was a dry powder that required no special handling or storage. This design philosophy reflected Patton's understanding that technology succeeds or fails based on the environment in which it must function. A welding system that worked perfectly in a modern factory with trained technicians and reliable power would fail catastrophically in Nizhny Tagil, where temperatures swung from 30 below zero in winter to 40 above in summer, where electrical power was irregular, and where operators might be teenagers who had never seen industrial equipment before. The automatic welding machines worked because they were designed for the reality of Soviet industrial conditions, not the ideal conditions described in engineering textbooks. The flux composition, refined through hundreds of test welds, became a carefully guarded specification. The mixture combined calcium fluoride, manganese oxide, ferromanganese powder, and small quantities of aluminum as a deoxidizer. When melted by the arc, these compounds created a molten slag that was denser than the steel weld pool and floated on top, protecting the liquid metal from atmospheric oxygen and nitrogen. The slag also controlled cooling rate. Slow cooling allowed hydrogen to diffuse out of the weld before the metal solidified and allowed internal stresses to relax. Fast cooling, which created the hard, brittle microstructures prone to cracking, was prevented by the insulating effect of the molten flux blanket. The wire electrode specification was equally critical. Low-carbon steel wire with less than 0.05% carbon was produced at specialized mills in the Urals. The wire diameter was 5 mm, thick enough to carry high welding current without overheating, but thin enough to feed reliably through the machine's drive mechanism. The wire surface was copper-coated to improve electrical contact and prevent rust, which could introduce contaminants into the weld. Quality control on the wire was obsessive, because a single bad spool could ruin dozens of hulls before the problem was identified. The welding parameters, amperage, voltage, and travel speed, were standardized across all machines and all factories. 600 amperes at 32 volts, traveling at 30 centimeters per minute. These settings had been determined through systematic experimentation in which every variable was tested across its practical range. Lower amperage produced incomplete fusion between the weld metal and base metal. Higher amperage created excessive heat input that altered the armor's heat treatment. Slower travel speed deposited too much weld metal, creating high residual stresses. Faster travel produced undercut and poor bead shape. The optimum parameters represented a narrow window where multiple conflicting requirements were balanced. Training for machine operators focused not on welding theory, but on practical troubleshooting. Operators learned to recognize when feed rate was incorrect by listening to the sound of the arc. A smooth, consistent hum meant everything was working correctly. Sputtering or popping indicated feed problems that required adjustment. They learned to recognize when the flux hopper was running low by watching the slag formation. They learned to detect incomplete fusion by examining the slag pattern after the weld cooled. The training was empirical and pattern-based, rather than theoretical, perfectly suited to operators who had minimal formal education but good observational skills. The inspection process for completed hulls became increasingly sophisticated as production volumes grew. Magnetic particle inspection revealed surface-breaking cracks by applying iron powder and a magnetic field to the weld area. Cracks disrupted the magnetic field lines, causing powder to accumulate in visible patterns. Ultrasonic testing used high-frequency sound waves to detect internal defects that visual inspection could not find. A technician placed a transducer on the weld surface and monitored echoes on an oscilloscope screen. Voids, lack of fusion, or cracks produced characteristic echo patterns. Hulls that passed inspection were proof-tested by firing anti-tank rounds at representative armor sections. This destructive testing was done on a sample basis, approximately one hull in every 100, but it provided crucial feedback about whether the armor's ballistic performance matched specifications. Test results showed that properly welded armor performed identically to unwelded plate. The welds themselves, being softer than the hardened armor, did not create weak points. In fact, the softer weld metal sometimes arrested cracks that initiated in the brittle armor, a beneficial effect that engineers had not anticipated. The production line at Factory 183 evolved into a carefully choreographed sequence. Armor plates arrived by rail from the steel mills and were immediately inspected for thickness, hardness, and surface quality. Plates that passed inspection were cut to shape using plasma cutting torches, a process that was faster and more precise than mechanical shearing. The cut plates were then assembled into sub-assemblies, lower hull sections, upper hull sections, turret components, using temporary tack welds to hold everything in alignment. These sub-assemblies moved to the automatic welding station, where 19 machines worked simultaneously on different components. The machines ran continuously, pausing only for operator breaks and slag removal. Each hull required approximately 40 linear meters of welding. At 30 centimeters per minute, this meant 80 minutes of arc time per hull, plus setup, repositioning, and inspection. A complete hull moved through the automatic welding station in approximately 4 hours. After welding, hulls were moved to stress relief ovens. These massive brick-lined structures, heated by coal-fired furnaces, brought the hulls to 600 degrees Celsius and held them at temperature for 2 hours. This heat treatment allowed residual stresses to relax through thermal creep, reducing internal stresses by approximately 70%. The hulls then cooled slowly over 8 hours. This stress relief process added time to production but virtually eliminated late-stage cracking failures. Hulls that emerged from stress relief were dimensionally stable and ready for final machining and assembly. The impact of automatic welding extended beyond Factory 183. By mid-1943, the technology had spread to Tankograd in Chelyabinsk, the Krasnoye Sormovo factory in Gorky, and the Uralmash plant in Sverdlovsk. Each facility implemented the system with minor variations adapted to local conditions and available equipment. Tankograd, which produced KV-heavy tanks in addition to T-34 seconds, used automatic welding for the lower hull sections, where seams were long and straight. The KV's hull bottom required approximately 15 linear meters of welding per tank. Automatic welding reduced production time from 8 hours to 90 minutes. The Krasnoye Sormovo factory, located on the Volga River, specialized in cast turrets rather than welded ones. They used automatic welding primarily for hull assembly, but developed techniques for welding cast armor to rolled plate, a challenging metallurgical problem because cast and rolled steel have different microstructures. Their solution involved preheating the cast sections to 300 degrees before welding, which reduced thermal shock and prevented cracking at the dissimilar metal interface. Professor Paton's team at the Institute of Electric Welding continued refining the process throughout 1943 and 44. They developed multi-wire welding heads that deposited weld metal from 2 electrodes simultaneously, doubling deposition rate. They experimented with alternating current versus direct current, finding that AC reduced magnetic arc blow, a phenomenon where magnetic fields deflected the arc and created irregular bead shapes. They tested dozens of flux formulations, optimizing for different steel chemistries and welding positions. One particularly important innovation was underwater welding for hull stress relief. At Nizhny Tagil, engineers discovered that submerging freshly welded hulls in water tanks accelerated cooling and actually reduced cracking compared to air cooling. This seemed counterintuitive since rapid cooling usually increased cracking risk, but the water provided uniform cooling across the entire hull, preventing differential contraction that created stress concentrations. The technique was implemented cautiously. Only after extensive testing confirmed it did not compromise armor properties, but it eliminated the need for slow air cooling, saving 8 hours per hull. The workforce transformation was equally profound. Women, who constituted less than 10% of Soviet metalworking labor in 1941, comprised over 50% by 1944. Many worked as automatic welding operators, a role that required technical understanding but not the physical strength demanded by hand welding. The Soviet propaganda machine celebrated these women as heroes of socialist labor, and while the rhetoric was predictable, the underlying reality was revolutionary. Industrial capability that had been gender-restricted for the entire history of metalworking had suddenly become accessible to half the population. The youngest operator at Factory 183 was Anna Mikhailovna Ivanova, 16 years old in October 1942, when she completed her 1-week training. She operated machine number 7, which welded the starboard side hull seams. Her production logs show she completed an average of 6 hulls per 12-hour shift, with a defect rate below 2%. This productivity matched or exceeded that of experienced male welders. When interviewed after the war, she recalled that the machine did most of the work. Her job was to watch, listen, and intervene when something went wrong. The machine made her competent. Before the war, such competence would have required 5 years of apprenticeship. The German response to Soviet production volumes reveals how completely they misunderstood the situation. German intelligence reports from 1943 estimated Soviet tank production at approximately 8,000 units annually, roughly half the actual figure. They assumed the Soviets were using traditional production methods, but with more factories and longer working hours. The possibility that the Soviets had implemented automated manufacturing techniques superior to German methods was not seriously considered. German engineers visiting captured Soviet factories in occupied territories found the automatic welding equipment, but dismissed it as crude and unsuitable for quality production. This technological arrogance cost Germany dearly. German tank production in 1943 could have been substantially higher if automatic welding had been adopted. The Germans had the metallurgical expertise to solve the armor-cracking problem and the manufacturing capacity to build welding machines, but they never made the attempt because their military procurement system valued craft perfection over mass production. A hand-welded Panther tank with its aesthetically beautiful weld beads was considered superior to a machine-welded T-34 with its rougher appearance. This preference for craftsmanship over quantity was philosophically German and strategically fatal. The final production numbers told a story of industrial might that overwhelmed tactical and technical superiority. Between 1941 and 1945, Soviet factories produced 57,300 T-34 tanks. This represented more tanks than Germany, Britain, and the United States combined produced in the same period. Automatic welding, developed under desperate circumstances in evacuated factories, had given the Soviet Union a production advantage that no amount of German tactical skill could overcome. The irony was profound. The Germans, whose early war success came from mechanized warfare and industrial efficiency, were defeated by an opponent who mechanized tank production more effectively than they had mechanized warfare. The T-34, individually inferior to late-war German tanks in armor protection and firepower, won through sheer numerical superiority. And that numerical superiority came directly from Patton's automatic welding system, which transformed tank production from a craft to an industrial process. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.